So this is our project for discussing three applications of derivatives and integrals in other fields, and this is written by Diego and Siddharth. The first application is going to be motion profiling in robotics. The problem statement says that in robotics, actuator-controlled movements can result in rapid change in acceleration. Jerk is the derivative of acceleration with respect to time. Jerk can result in damage to fragile components, especially electronics and motors. It creates movements in humanoids that do not accurately depict reality. To minimize jerk, we need to first quantify it. The robot's path is modeled by a position function, where S of t is t cubed minus 6t squared plus 9t over a distance of 0 to 4. Identify time intervals where jerk is large and discuss how the robot's motion can be controlled. And the theory is that motion profiling is a control technique used in robotics to generate smooth, realistic movements. Minimizing jerks make the movement smooth, called S-curve shapes. We also need to understand the derivative relationships with respect to time. S of t is position, S prime of t is velocity, and V prime of t is acceleration. And what we're looking for is the A prime of t in acceleration, which is jerk j of t. This is our calculation where you basically apply the derivative until you get your jerk, your j of t, which is the derivative of the acceleration. Here's our visualization and the key here. We have the blue line, which is the position time, black line, which is our velocity time, red line is our acceleration time, green line is the jerk time, which we were looking for, and the purple region is our closed interval between 0 and 4. Our second application is work done by a variable force. The problem statement is, in terms of oscillating resistance, a force is acting on an object according to 10 sine of 2x plus x squared, 6x squared, with x representing the distance in meters. In this case, we want to find out how much work is done in displacing the object from 0 to pi over 2 meters. Integrals can be applied in this problem, as finding the work by a variable force over a displacement can be found by taking a definite integral over a set amount of distance. Finding the integral of 10 sine of 2x plus 6x squared over a distance of pi over 2 to 0 will outline the total work done in joules. So here's our calculation. What we did basically was we took the integral, the definite integral of 10 sine 2x plus 6x squared over pi over 2 to 0, and we found that it was 17.75 joules over that interval. This is our visualization. Purple line is going to be the x equals 0. Green line is pi over 2. This is our interval. And the red line is the original function. And our final application is optimization of a loss function in machine learning. The problem statement is a machine learning model, such as LLMs, has a loss function describing prediction error on a tunable parameter. L of x is 2x cubed minus 9x squared plus 12x plus 10 over interval of 0 to 3. We want to find the value of x in the given interval that minimizes loss. Let's assume that the loss is modeled as a single variable function. And the theory is that LLMs are trained on huge datasets in order to predict the next word in a sentence. A loss function quantifies the error gap between a model's prediction and the true value. Machine learning seeks values of parameters where this error gap is the smallest. Model the loss function as a single variable curve and find the absolute minimum in a closed interval. The parameter x at this point is where the lowest error gap is found. Absolute extrema in a closed interval can be of two types: endpoints and critical points, which occur when L prime of x is equal to 0 or undefined. 0 divided by undefined. These points may be local maxima, minima, or undefined, discontinuities, vertical tangents, and sharp corners. This is called the closed interval method. Here's our calculation, where we found the derivative, we factorized, we found the critical points from getting the derivatives, we find the endpoints, and then we identify the absolute minimum from taking the highest amount of critical point. Here's our visualization. Point 0 to 10 is our absolute minimum. Point 1 to 15, 1 to 15 is our local maximum. 2 to 14 is our local minimum. 3 to 19 is our absolute maximum. Red line, L of x, loss function. And our purple region, which is the closed interval between 0 and 3. This is our bibliography, and thank you for watching this presentation.